Thahira from the Department of Remote Sensing, Badasan University. So I'm here to do my poster multimedia presentation on the topic Geomorphic Analysis of an Unnamed Crater in the Diarcia Quadrangle Mars for the presence of water ice signatures using Sharad Radargrams. Heading off to the introduction. So the glaciation activity was prominent on Mars, especially from the Amazonian period, and this water ice is not stable currently in mid-latitudes. During the obligatory cycle, the stable portion of the ice which was present in the mid-latitudes assumed to be preserved beneath the low-bit debris aprons, also known as rock glaciers on Earth. So this ice deposition keeps on varying depending upon the obligatory cycle and the seasonal variation in the axial tilt of the planet's mass. Now this mass has solid gas exchanges for both CO2 and water H2O volatiles, depending upon their frost points and the temperatures prevailing. And although it has a high dependence on the latitudes. Now these polar ice caps on the high latitudes have temperatures lower than the CO2 frost point, so it facilitates CO2 ice deposition on polar regions. Whereas at the mid latitudes, the temperature conditions are more feasible for water ice frost deposition and is very thin compared to CO2 ice due to low presence of water vapor. These are the information which is derived from the literatures. So there's a possibility for all these facts. This does modify the geomorphic surface with minor and major terrain patterns. Like minor are PT, Novi, and brain terrains, etc. And major ones are like LDAs, LDFs. LDAs means low bit debris aprons, and LVS means lineated valley fills, etc. So these are the images or the collected from the literature, Mangold et al. So this is an image of an PT terrain and Nobi terrains. And this is an image of an PT terrain observed over a low-bit debris aprons from a high-rise image. And this crater you are saying is much altered or degraded by or affected by those PT terrains. So this is a process of those possibly the formation of these terrains. It is the slow ice sublimations with ice and solid grains. These sublimate and that tend to create fractures, and the solid ice grains within those fractures also sublimates, creating a cliff regression and then raising of loose dust. So these are data sets and methodology used in this study. MRO CTs images, high-rise images, and Sharad Radargrams and molar den. This is the study area. This is an unnamed crater located in the location coordinates in the Diarcia Quadrangle. It's approximately 47 km in diameter and is approximately 300 km away from the Acheron fossé to the north. And these are the impact craters, and the purple one are the lobate features, central peak. The blue ones are the low-bit debris aprons, etc. And the black, the line which are seeing in the map is the radargram path, which is used in this study. So these are the observation and discussions regarding the geomorphic analysis. As I said before, the crater is approximately 47 to 48 km in diameter. It has a central peak on 150-meter height, and it has impact melt spreading 10 km across the crater. The crater wall is around 200-meter to 700-meter height varying. The central peak is encompassed by the pit floor and impact melt, and this crater is subjected to rapid resurfacing, which is observed can be guessed by the numerous ghost and highly degraded craters affected due to the PT terrains. So those craters are mapped approximately 525 in count, visualized using the CraterStat tools in ArcMap. And these crater has the glacial flow-like features like rock glaciers on Earth, which are analogous to Martian LDAs. So this LDA, which is shown in this map, now has the kilometer span area of around 265 kilometers, the highlands and the LDA and the LDA terminal lobes and the lobate features in between. And this is the central peak, central pit floor, impact melt, and the marginal pit floor. And this is the image of the lobate features and some of the craters mapped and the radargram path. So there are very feeble presence of fresh impact craters in the LDA, which indicates the activeness of the region. And this is the terrain characteristics which we had discussed even before the introduction from the through the literatures. So this is an ablation hollow-like structure or sun cup-like structure from the observed in the PT terrain, which has affected the craters which have formed before. And this is the brain terrain, and this is the again the PT terrain. So as our studied a crater possess these patterns all over the crater floor, it is further supposed the possibility of existence of ground ice beneath the crater. These are the Sharad radargrams. So our crater lies exactly in the beginning of the radargram, making it easy to identify and locate. These subsurface reflections result from the contrast in the dielectric permittivity across different media or geological sections. So the water ice shows distinct radar reflections in a radargram with the dielectric constant of around 3 to 3.2. So even I processed these images I tried processing these images in the CoSharp's processing boutique from the Planetary Science Institute with the dielectric constant of this 3 to 3.2, and it supported the reflections of it may possibly be a water ice. So these are the simulated images of the same radargram downloaded from the Mars OD website, and this is the zoomed in version of the radargram, and the arrow marks are possibly indicating the presence of water ice signatures beneath the crater. So here we are in the conclusion. So based on our analysis of the crater's geomorphology, subsurface and related literature, we strongly believe there are ice deposits located beneath it, and we suggest the possibility of those things. Our study supports the presence of ionic sublimation activity occurring throughout its terrain patterns. The crater has been greatly impacted by petty terrains throughout, indicating the removal of a uniform ice background that was present before. The presence of these viscous flow features, lobate debris, aprons, and other glacial-like features further supports our findings in this craters about this crater. So these are the references, some of the references, and let me know your suggestions. Thank you.
So thank you very much for your presentation. So any question from audience? Okay, so there is no question from audience, so I may ask one. Am I audible to you?
Yes, sir, you are.
How are you determining the dielectric constant for that part that is I maybe missed?
Actually, yeah, so that is according to the literatures through Head et al. And some of the 2 or 3 literatures, which really explain those dielectric permittivity, and they have researched and they have used those constants, and they have proved that okay, they have found bulk ice beneath these regions in Detroit, Mense, and other regions of Mars. So it is really 2 to 3 papers which just works on this using subsurface ice identification using Sharad radargrams.
Okay, so you are not retrieving the dielectric using any other methods, right? Not from the radar.
No, it's Sharad radargrams are highly complex. I'm not retrieving it. No.
Okay, thank you very much.
Yes. There's a question in the chat box. Can I answer? No.
Yeah, you can answer it. How do we determine whether it is CO2, ice, or water ice?
Now, in terms of geomorphic analysis, there are different terrain patterns. Like what did I show in this presentation? Let it be the PT terrains or the sort of knobby terrains. They usually may indicate the water side signatures. And there are specific patterns for CO2 ice itself. Like they are called as spiders. It will be like a sort of a radial fracture like thing, but they are not fractures. Those are types of patterns they also indicate, and also for further investigation you have to do the mineralogical analysis using CRISM for that same particular spectra.
Good afternoon. My name is Poorva Singh, and the topic for my poster multimedia presentation is Evaluation of Chandrayaan 2 IIRS Data for Moon Surface Exploration. This evaluation is performed using hyperspectral data. Hyperspectral data have a high resolution and is one of the most useful resource for lithological and mineralogical mapping of Earth and extraterrestrial objects. India's moon mission have sensors that provide hyperspectral data such as Chandrayaan-1 Moon Mineralogy Mapper and Chandrayaan-2 Imaging Infrared Spectrometer. The objective for this research is to analyze Chandrayaan-2 data for mineral detection and identification on the lunar surface and evaluating the results with the results obtained from Chandrayaan-1 M-Cube data. A small lunar impact crater named Gobbler is selected for this study. It is an impact crater centered at 11.5 degree north and 142.6 degree east on the moon's far side. The radiance product of Chandrayaan-2 IRS data and reflectance products of Chandrayaan-1 M-Cube data with the following specifications were used in this study. The IRS radiance product was first converted to reflectance and both datasets were referenced in moon data. The datasets were then subsetted spatially and spectrally to focus on the study area with a common spectral range. Spectral analysis and band shaping algorithms were applied for the mineral identification. 4 band parameters, that are band ratio, band tilt, band strength, and band curvature, were calculated for both the datasets. The band parameters are derived for M-cube datasets. Thus, in order to perform a comparison, IRS bands closest to M-cube bands were used to calculate band parameters for IRS datasets. The spectral profile from different locations from both sensors were compared. Here, IRS spectral profiles are found to be more detailed, especially at the 1300 nanometer and 2500 nanometer absorption regions than the M-cube spectral profile. The bright areas in bright regions in the grayscale image for band ratio parameter shows the presence of olivine mineral that is outside the crater and at the crater floor, with blue color showing the presence of anthracite rocks or weathered rocks in the band parameter false color composite. The yellow color in the M-cube and green color in the IIR dataset shows the presence of high calcium pyroxene with the pink to magenta shades indicating the low calcium pyroxenes. This study concludes that the spectral curvature of different minerals in Chandrayaan-2 IRS data shows absorption in more details because of better spectral resolutions than Chandrayaan-1 M-cube data. Band shaping algorithms enable identification of olivine-rich minerals and weathered rocks perfectly on the crater floor and outside crater. The presence of both high calcium pyroxene and low calcium pyroxene is identified on crater walls, rims, and central peak using band parameters of hyperspectral data. The band shaping algorithm was found as an effective technique as wall color composite generated from the band parameters were able to identify minerals very clearly in the lunar surface. IRS data having a better spectral resolution provide more precise mineral identification in and around the Gobbler crater in comparison to M-cube data. Here we will have to show our thanks and gratitude towards ISRO Space Data Archives for providing Chandrayaan-2 data and PDS Geosciences Node for providing Chandrayaan-1 data, and also to Director IIRS ISRO for providing their guidance and support. Thank you.
Good evening, everyone. I am Pritipadmaja from IIT Roorkee. Here, I am presenting our research paper on Mapping Persistent Urban Heat Islands, a decadal study of land surface temperature pattern of Bhubaneswar. My co-authors are Rohit Sharma, Dyutisree Halder, and Professor Rahul Devkar from IIT Roorkee. Urban development and climate change have led to the emergence of urban heat islands, that is UHI, which has become a research interest in recent times. Studying how cities change helps us to understand the UHI effect, guiding better city planning and climate strategies. The objective of this study is to understand the presence, variation, and persistence of UHI in Bhubaneswar. What is UHI? UHI or urban heat island is the increased temperature within urban environment compared to the surrounding areas, forming as thermal pockets within the city. Its effects have wide-ranging consequences on human health, energy consumption, and the environment. With increasing urbanization and climate change, Bhubaneswar, capital of Odisha, faces the challenges of heat waves and the UHI effect. So, for this study, we have taken Bhubaneswar Municipal Corporation for the persistence of UHI analysis. In this study, we have used Landsat 8 and 9 datasets, both top of the atmosphere reflectance and surface reflectance collection from 2013 to 2023. Acquired during summer months for better thermal stress and no cloud cover. Here are the dates of the images which are of March and April for each year of the study period. For LST estimation, first we masked clouds and filtered both of the collection of Landsat to date range and study area. Then NDVI, that is normalized difference vegetation index, and fractional vegetation were calculated from the Landsat surface reflectance collection. Emissivity was calculated from the top of the atmosphere brightness temperature collection. Then LST was calculated by a single channel algorithm. Here are the results of estimated LST for each year from 2013 to 2023 as shown in the GIF. For UHI delineation, from the estimated LST of each year, we have plotted the histogram. And after careful observation, we have delineated UHI for each year as mean plus 0.5 into standard deviation. Then all these 11 UHIs were aggregated together to get the frequency UHI map. This UHI frequency map offers insight into the cumulative UHI patterns throughout the last decade, hence further guiding subsequent analysis. Here in the map, we can see the UHI frequency within the urban environment of the last decade. Areas colored dark red and brown are the most frequent UHI in the last decade. The frequency UHI map serves as a valuable resource for examining the long-term persistence and spatial distribution of UHI phenomena. Further, areas showing persistent or highest frequency UHI areas, that is 10 and 11 years of UHI presence, were identified and delineated, warranting specific attention and mitigation efforts. Highest frequency UHI areas are mainly bare land because of lack of vegetation cover. They exhibit persistent UHI. Bhubaneswar Airport. This airport characterized by a combination of open, bare land spaces and built-up structures, hence exhibiting persistent UHI. Mancheswar Industrial Zone. This area is a built-up zone with mostly have steel and asbestos roofs, hence exhibiting persistent UHI. Sandy patches along the Kuakhai River which is a dry bed and hence exhibiting persistent UHA. In Bhubaneswar, persistent UHI mainly associated with bare land, open land spaces, and industrial areas. This understanding provides a foundation for informed strategies aimed at mitigating UHI effects and promoting sustainable urban development. Coming to conclusion, this study examines a decadal study from 2013 to 2023 in order to get the deeper understanding of the intricate relationship between urban environment and temperature dynamics. This work enhances the scientific understanding of the UHA phenomenon and offers vital insights for urban planning and climate adaptation methods in rapidly expanding cities. Geospatial analysis methods of an advanced kind, together with the use of remote sensing data, are employed in the examination of UHA trends, spatial patterns, and the extent to which they endure in relation to urban growth. Coming to solution, there are a number of short-term and long-term solutions to adopt to mitigate some of the urban heat stress. Incorporating water-sensitive urban design and implementing strategies in urban areas can mitigate adverse UHA effects. Some of the measures we can take like planting trees, green roof or rooftop garden, cool roofs, and cool pavements. So here are the references. And thank you all.
Good afternoon, everyone. Today, I'm glad to discuss our paper titled Multitemporal Analysis in Google Earth Engine for Detecting Urban Changes Using Optical Data and Machine Learning Algorithms. In this slide, the authors of paper are presented along with their respective and key information. Let us now turn our attention to the overview of this presentation. I will provide an initial summary of the introduction to the problem and the significance of this study, highlighting the aims and objectives. I will then move on to the section titled Google Earth Engine and Data Sources, where I will briefly address the context of Google Earth Engine platform and the Landsat aims. After, I will delve into the region of interest and machine learning model, proceeding with the classification and change detection process. Finally, I will report the results derived from the previous step. Today's urban planning integrates traditional methods with advanced techniques like remote sensing, machine learning, and deep learning. Machine learning and deep learning are crucial in handling vast satellite data, enhancing classification analysis, land use monitoring, and natural phenomena detection. Detecting changes in urban or urban areas are vital for predicting future expansion and assessing environmental and economic impacts. The fusion of remote sensing and advanced computational methods is transforming urban planning, providing valuable insights for informed decision-making by governments. In our research, we focus on utilizing optical satellite data and specific machine learning algorithms through the Google Earth Engine platform for a multi-temporal analysis of urban changes. The study's core involves applying change detection to nearly 10 years of remote sensing images, specifically targeting urban variation not easily discernible through official documentation or sample surveys. The research spans from July 2013 to July 2021, incorporating classification and change detection analysis of the region of interest to monitor urban growth. The results affirm the efficacy of the proposed method in accurately identifying changes in urban areas throughout the specified period. Google Earth Engine is a free cloud-based platform for processing extensive remote sensing data globally. It offers access to a different range of satellite images, empowering users to detect changes, monitor the atmosphere, map trends, and quantify surface differences. In our study, we utilized the Google Earth Engine package for supervised classification, specifically employing the Garg tool. This algorithm employs decision trees based on if-else rules to predict outcomes from other quantities. The smart machine learning algorithm was then applied to Landsat data focused on Cairo city's urban agglomeration, serving as the region of interest. The goal was to enhance change detection and monitor urban growth in the specified area. In this slide, the main features of Landsat 8 mission are outlined. Specific reference is made to the bands and technical characteristics. As previously said, the objective is a multi-temporal analysis of urban changes using Google Earth Engine and machine learning algorithms, with Cairo City chosen due to its status as one of the world's 5 most populous megacities over the last decade in Egypt. The selected area serves as the focal point for the proposed method, aiming to provide a time-based analysis. The objective is to determine changes in the urban landscape, including expansion, stability, shifts between urban and non-urban designations, or the persistence of unchanged area. As reported in the block diagram on figure, in our study, we selected the region of interest as a Cairo city with specific coordinates. An image from Landsat 8 for the oldest date in the chosen time period, July 2018, was used to create a dataset for training the model, ensuring cloud-free conditions. A future collection was generated, and this phase is in dataset creation. The smart card classifier was chosen and instantiated, and its parameters were configured. The classifier was then trained with the created dataset in the training model phase. Finally, the trained model was employed for predicting land cover across all other images from 2018 to 2021 in a prediction phase. The outcome of this process is presented as classification maps. Once the classification data for each year have been acquired, we proceeded with the change detection step by considering the oldest classification and the most recent one to detect in a large period of time changes or invariances and using intermediate years for additional checking and comparison. There are 4 possible results. The first one is the case where there has actually been an expansion of the urban agglomeration, and this is reported as a red color. The case in which there was no expansion of the urban agglomeration and that just remained the same as it was on the older date considered, and this is in color purple. The third case is where an originally urban environment became non-urban, and this result is represented as blue color. And finally, the case where an originally non-urban environment is still not urban and undergoes no change, and this result is reported as green color. In these slides, I reported the first 2 results. The first one is the case of an expansion of the urban agglomeration referred to the red color in a colored image. In the picture on the right is Assam City. The second case is the invariance of the urban agglomeration referred to the purple color in a colored image. In this picture on the right is reported Tanta City. Here in this slide, I reported the last 2 results. The first one is the case where an urban environment has become no urban, referred to the blue color in the colored image. In the pictures on the right is a fraction of Tanta City. The last one is the case of a no-urban environmental invariance, referred to the green color in the colored image. In the pictures on the right is the Nile River. In these slides, you can find all the references. Thank you for your attention.
Yeah. So you have mentioned that there are many ML algorithms available in that suit, but you have opted for this classification and regression tree. So is there any specific reason for adopting this kind of algorithm?
We analyzed also the other one, but based on the state of the art and the other works, it seemed that the algorithm that in the end we chose is very efficient and also very easy with respect to other one. So we wanted, to demonstrate that with an easy algorithm inside the Google Earth Engine, it was possible to have these results. But in the future, our idea is also, to make something more like other comparisons with the other algorithms and also perhaps to choose different techniques.
Okay, yeah, thank you.
You're welcome.
Yeah, next we'll move on to paper number 86, integration of Sentinel-1 and Sentinel-2, data for Earth science, Earth surface clarification using machine learning algorithms implemented on Google Earth Engine.
Good afternoon to everyone. Today, I'm glad to discuss our paper-titled integration of Sentinel-1 and Sentinel-2 data for Earth surface classification using machine learning algorithms implemented on Google Earth Engine. In this slide, the authors of paper are presented along with their respective and key information. Let us now turn our attention to the overview of this presentation. I will provide an initial summary of the introduction to the problem and the significance of this study, highlighting the aims and objectives. I will then move on to the section titled Data Sources and Processing Environment, where I will briefly address the context of Copernicus Sentinel-1 and Sentinel-2 mission and the utilization of Google Earth Engine platform. After, I will delve into the area of interest and the machine learning model, proceeding with the creation of dataset and the proposed methodology for classification and validation. Finally, I will report the results derived from the classification and validation procedures. In remote sensing research, the integration of multimodal input data is essential to address the intricate nature of natural phenomena. Singular modes often fall short in providing a comprehensive understanding. The essence of multimodality lies in extracting and combining crucial information from individual sensors to tackle specific challenges, resulting in more comprehensive outcomes compared to individual modes. Several studies have explored the merging of SAR and optical satellite data, showcasing improved Earth surface classification. Our aim and scope in the study focuses on integration of SAR and optical data for Earth surface classification, specifically utilizing Sentinel-1 and Sentinel-2 data. We employ supervised machine learning on the Google Earth Engine platform to classify a designated region of interest. The implementation of machine learning algorithms on Google Earth Engine, coupled with the result validation, aims to enhance accuracy, validating our initial hypothesis. Satellite data from the European Space Agency Copernicus mission is utilized, and the Google Earth Engine environment facilitates data downloading and processing. The results underscore the complementary nature of radar and optical remote detection, providing valuable information that enhances surface cover classification and overall improves mapping accuracy. Additionally, this paper contributes to emphasizing the growing significance of Google Earth Engine as an efficient cloud-based tool for managing large volumes of satellite data. In this slide, the main features of Sentinel-1 and Sentinel-2 missions are outlined. Specific references are made to the bands and technical characteristics. The Polar Orbiting Radar mission is capable of operating day and night in all atmospheric conditions, providing observation services for both land and sea. The multispectral optical mission in polar orbit is dedicated to high-resolution monitoring of the territory, supplying images of vegetation cover, soil, and water. Among the advantageous features on Google Earth Engine, we employ supervised classification using traditional machine learning algorithms within the platform. Specifically, we choose the CART tool, a predictive model based on if-else decision rules. This tool offers several benefits, including versatility with response types. In Google Earth Engine, machine learning model training involves structuring training and test data as a feature collection. During classifier training, specify the class label's name and a list of properties in the training table is essential. Following training, the classifier proceeds to classification and validation. Google Earth Engine emphasizes the significance of validation step in the classification process, enabling the analysis of classification accuracy. An error matrix is generated, facilitating the process analysis and the calculation of the accuracy of individual classes. In our study, the area of interest chosen as a benchmark for the analysis has been a very fast-growing area in the USA, Texas City and its suburbs. Starting from the Texas City coordinates, it was possible to select and collect a series of Sentinel-2 images of the area of interest to create the dataset. We establish a time period and 6 bands of the images with the less cloud coverage. After dataset preparation, the card classifier has been selected and trained. We choose to analyze 3 classes, water area, urban area, and no-urban area. For each class, the number of samples used for training is reported in table. Therefore, the first classification of the area of interest was carried out based only on Sentinel-2 images. After that, the dataset was extended and Sentinel-1 data have been retrieved over the same time period. SAR bands have been integrated with the optical bands to create a composite image, on which they proceed with a new classification. In figure, the general workflow is represented. To obtain the fusion of different images, some operations have been performed to make it possible for the classifier to use both optical and SAR data. The final composite image is a stack including the band Sentinel-1 images and the Sentinel-2 images. For the validation, the table provides the count of samples utilized for each class during the validation step, which class samples are manually selected from the image of interest. The accuracy values are extracted from the confusion matrices. Sentinel-2 data on its own yields a precision of 81.7%. However, through the integration of optical and SAR data, precision improves significantly to 88.8%, as detailed in the following section. For the results, account should be taken of the fact that red zones identify no-urban areas, those in white identify urban areas, and finally the blue zones identify water areas. If we see the first example, it is possible to notice that image B cannot keep track of all regions of water, while image C takes into account most of the water regions side with the blue color indicators. This wants to give a first example of how the classification could benefit from composite images. It is noticed in the second example that the water areas have not been directed correctly. On the contrary, referring to the area of the left side of the images, for instance, they have been classified as no-urban areas since they appear in red color. It can also be noticed that the water curves in the original images are not correctly identified as a water zone in the image with only optical data. In fact, it is classified as a urban area with the color white. All these issues appear solved in the case C. Finally, the integration of optical and SAR data has been demonstrated to significantly enhance the quality of classification, and this is also shown for the results that we see previously. In this slide, you can find the references. Thank you for your attention.
So you have like the classes you have considered, the urban, the non-urban, and the water areas. So we'll say these are broad classes. So whether Sentinel-1, like the SAR data, wasn't itself sufficient to classify these areas with a good accuracy? Like you got an improvement from 81 to 88% combining S1 with S2. From S2 to S1, you got an accuracy improvement of 8%, I will say. So whether
Yes.
did you experiment not only with the Sentinel-1 data and you were because your classes are very broad, so you could have classified with that only? Any insight on that?
You are saying if we tried to use just SAR data, just Sentinel-1?
Yes, yes.
We didn't, honestly. We started with Sentinel-2 optical data, and then with this stack of Sentinel-2 plus Sentinel-1. I thank you for this suggestion. Maybe in the future, we can try to see what happens only with the SAR data.
Okay, okay.
Thank you.
Have you used any kind of pre-processing on this R data before fusion for speckle noise removal or suppression or something like that?
In our case, we retrieve the images directly from Google Earth Engine, and everything is inside this platform. Usually, when we use
I was just
Snap,
asking because that could improve the classification accuracy in that case.
no, we didn't do any pre-processing.
Okay, fine.
Okay, so thank you very much for your presentation. And
Before moving to the next presentation, I would like just to thank all of you for this amazing organization for the conference, and our friend Ujival that is there is part of the organization, and also our co-author that is Yogesh, and he lives in Bangalore. So for us was a little bit complicated this time to move from Italy, but we want to say hello and thank you to all of you there. Let's hope
thank
to
you.
be there with you next time. Dear Yogesh, thank you to be there.
Thank you. Thank you. Thank you, Ujjwal sir.
And thanks to all the organizers, because I mean, I can see that everything is perfect.
Okay, thank you very much. And now moving on. I would like to call paper number 184, Noise Analysis and Velocity Uncertainties of Multi-GNSS Time Series.
Good afternoon to everyone and all present here. Myself, Meenal Bodke. I am thankful to give me this great opportunity to present my paper here in this flagship conference, that is InGARSS. So the title of my today's presentation is Crypto Watermarking Scheme for Secure Transmission and Protection of Satellite Images. Myself, Meenal Bodke, and Dr. Sangeeta Chaudhary ma'am. So before starting with the topic, I would like to introduce the topic. So in today's era of internet technology, a huge amount of information is transmitted over the network. So there are n number of communication medium through which we can transmit the information or exchange the data. So one is audio, video, and images. So according to the research, we can find that images are predominantly used as a medium for information sharing. So there are n number of variety of images used for wide variety of application. So our research mainly focus on satellite images. The satellite images are collected from many resources like topographic maps, aerial sensors, satellite sensors, positioning system, and ground-based observation. As we know this, satellite images are used in wide variety of applications such as defense, military, agriculture, natural calamities, oceanography, and in weather forecasting. So it has n number of application in day-to-day life today. So the storage and sharing of the satellite images are very costly and time consuming, as we know. The satellite image consists of the confidential data which is exposed to various threats or attack when it is shared over the communication medium. So it can lead to a duplication of the images, the stealing of the sensitive data, but it can also alter the content in the data and utilize them illegally for illegal purposes or to cause some damage. So therefore, there is a need for demand for a secure transmission of satellite images. So as we can see in the image, we have the satellite images shown, which is captured through the Landsat data set. Now, as we know that there are n number of techniques to secure the images. So we can basically classify the security system in two main parts. One is we can hide the data which we want to transmit over the network. And second is a cryptographic technique where we can convert our data into ununderstandable format, that is a ciphertext format or cipher image. And then we can transmit over the medium where the attacker is unknown about the things which we are sending over the medium. So basically, in our research, we are going to focus on digital watermarking and the cryptography hand in hand to provide the entire security during the transmission and to protect the copyright protection of the data. So As the name suggests, we are going to use, we have designed a crypto watermarking scheme for protection and secure dissemination of satellite images. Now, let's move forward toward the proposed system. So, as you can see in the diagram, here we have a generic framework of the design system. So here in the first stage, there are two main stages here. One is the sender side and second one is the receiver side. So at the sender side, basically two main operations has been done. One is digital watermarking and second one is encryption of the image. So the input to the first stage will be the two images as seen in the diagram. One is the cover image. It means nothing but a secret image. And the second image will be input the watermark logo, which we are going to embed into the secret image for the authentication purpose or for copyright protection. Then we are going to apply 3-level DWT for watermarking, and after once we watermark the image, we have done the encryption by applying multiplicative cipher encryption technique, and the resultant will be the cipher image. Now this cipher image, as you can see in the diagram, it is not in the understandable format. So this cipher image is transmitted over the network to the receiver. So the receiver will receive that cipher image and the reverse process will be carried out, and at the resultant end we will get our recovered cover image and the extracted watermark logo. So this is nothing but the theoretical concept of the proposed system. So basically, 3-level DWT used for watermarking technique. As we know that there are n number of methods available for watermarking, special domain and transform domain. But as we know that special domain watermarking is easily visible to the human naked eyes, whereas the transform domain has the advantage over the special domain that it is more robust. It is resistance against to many attacks. So we have gone with the transform domain, that is the discrete wavelet transform, which is more robust. So basically, we know that in 3-level DWT, image is divided into two frequency bands, low frequency band and our high frequency band. So in this way, the image is decomposed using a 3-level DWT, and then we have embedded the watermark into the cover image by using this mathematical equation as stated in equation number 1, where K and Q represent the scaling factor, LL2 and WM2 represents the low frequency band of the cover image and the watermark image. And here we have obtained a watermark image. And once we have obtained the watermark image, we have in the second step we have performed the encryption by using a multiplicative cipher technique, which is a very simple multiplication done. So here watermark image into the key according to the mathematical equation given in the 2. So in this way, we have received a cipher image, and at the receiver end, the process will be reversed. We are going to first decrypt the image by using the reverse, and then we are going to extract the watermark from the cover image. And at the resultant, as shown in the diagram, we have received two images, that is the reconstructed image and the watermark logo. Then next part is the result analysis we have done. So in the pic, you can see that in the picture, you can see that this is the sample image revealing, where the first input is the original cover image. Second one is our watermark logo. Then next, in the next row, we can see that we have a image we have obtained by applying 3-level DWT. And on the watermark logo also we have applied 3-level DWT. And in the third row, we can see the first image is a watermark image. Now on this watermark image, the next diagram you can see we have a cipher image where we have encrypted the using multiplicative cipher, and the last row represent the reconstructed original image and the watermark logo. So this experimentation were carried out for n number of images. So these are the sample images we have tried out, original and reconstructed, and good PSNR ratio was achieved. And good entropy value was achieved, which was near about 8. So in the conclusion, we can quote that we have developed a crypto watermarking technique for protection and secure transmission of satellite images. And in the future work, instead of embedding a watermark into the entire image, we can find out a suitable channel and optimal location for embedding the watermark, which will be less time consuming, as well as we are going to use the advanced encryption technique for encrypting. Thank you. And these are the references. Thank you so much. Questions? Yes, yes, 100%. Actually, this is a basic framework I have designed here, and currently I'm working on it. Where I have, instead of encrypting the image on the entire image, I have selected the band, and on that band I have applied the watermarking and attacks I have studied, like noise and filter attack I have studied, salt and paper noise. So I have result for that second paper also. No, no, in this I have not included that noise. Yes.
Encrypting the satellite data. So how is it different from encrypting any other image for security purpose?
If we take the normal images, which are of only three plane bands we have, RGB. But in case of satellite images, we have multispectral images and hyperspectral images, which have n number of bands. So encrypting this band is very tedious job. So for my this work, I have used normally three plane images, and currently I'm working on that, where I'm going to use deep learning model to encrypt that TIFF images.
If that there is some drop when you are reconstructing the image, like are the input image and output image
they are same, but I have not performed any attack here in my case. So that analysis I have not done. I have just checked the quality. So it is near more than 40%. Visual quality I have checked. And for encrypted, I have checked the entropy. This level I have checked. This all things I have done included in my next paper where it's going on currently. Yes. No, I will be working with multispectral as well as hyperspectral images. SAR images. Because this is actually, we have two methods, spatial and transform domain. And this 3WT is more robust against all the attacks, geometric and non-geometric attacks. And again, it is, you cannot see the watermark after embedding using 3WT. No, in the watermark image. Thank you. Thank you.
Next, I would like to ask paper number 272. Data processing for millimeter wave humidity sounder of EOS 07 mission.
Myself, Dinesh Kumar Jain from Space Application Center, ISRO Ahmedabad. In this session, I am presenting data processing element and data products for MHS payload on board to the US-7 ISRO mission. Earth Observation Satellite 07 has launched by the ISRO on 10th February this year to place it in 37-degree inclined circular orbit at the altitude of 450 km. It is equipped with two payloads, namely millimeter wave humidity sounder for 3D humidity profiling over the Earth's surface up to 12 km. The other one is a spectral monitoring payload, which is designed for RF sensing and surveillance. This presentation is limited to the data processing element corresponding to MHS data products only. Millimeter wave humidity sounder payload is a 6-channel total power radiometer system which is operated in vicinity of 183 GHz microwave frequency region. It is a water vapor absorption channel. The channel specification are mentioned on the table on this slide. The placement of this channel on atmospheric attenuation curve are presented through yellow columns. This payload has reflector feed assembly with cross-track scanning mechanism. The sample integration time is around 4 milliseconds. It covers the swath around 1050 km with Nadir resolution is around 10 km. This is the first time the ISRO has developed high frequency millimeter wave technology RF system. Levels of product. There are three types of products are defined for MHS payload data. First one is actual telemetry product. It is defined to preserve the actual data acquired by the payload along with the orbit and attitude parameter. The second one is a scan mode product. It is defined over the acquired geometry. There are two types of product are defined in this category. Level 1 is associated to the brightness temperature parameter. Level 2 is associated to the humidity profile parameter. All these products are generated after each and every dump acquired and archived. The global mode products are defined for consolidating these product parameter on the global grid of 0.1 degree interval. This product is archived twice in a day. All the product parameter associated to the different product are also mentioned on this slide. The ground segment interface is presented here. The onboard acquired data is downloaded at NRSC. Level 0 data processing is done at NRSC. The processed data is transferred to MOSDEC for high level of data processing. The level 1, level 2, level 3 products are generated at MOSDEC and archived. These archived products are available to the user through website hosted by the MOSDEC as mentioned on this slide. The green box presented over the image is presenting the area of interest defined for this mission. The passes outside this box are commissioned for inter-sensor data comparison. MHS payload receiver is a total power radiometer whose output voltage follows the linear model with respect to the input noise temperature. The model parameters are estimated at each and every scan level using the 2-point calibration data required over the scan. The brightness temperature corresponding to the given footprint is estimated using these parameters. The radiometric sensitivity of all the channel is validated using brightness temperature of reference black body on board. The brightness temperature of reference black body corresponding to all the channel are estimated using linear model mentioned in the previous slide. The sensitivity of the channel estimated confirming the specification and consistent throughout the operation carried out till day. The geolocation estimate corresponding to given footprint is processed by computing the intersection point of its line of sight vector with Earth ellipsoid. The accuracy of geolocation is validated using land sea boundary feature, which is clearly visible in video data. The MHS data products are validated using inter-sensor comparison scheme. We have used nearly co-temporal co-located ATMS sensor dataset mentioned over this slide. The channel correspondence between the two sensor has been also mentioned on this slide. The background image and foreground BT images in this slide represents the ATMS and MHS channel respectively. This confirms the geolocation consistency between the two. The radiometric temperature difference is maybe due to the bandwidth difference, incidence angle difference, and time difference. The generated level 1 product is displayed on this slide. It is processed at MOSTEC and archived in SDF5 format. The top right image on this slide represents the product in SDF5 format. The variability of BT over MHS channel has been displayed using Biparjoy cyclone acquired during 13 June 2023 over Arabian Sea near Gujarat coast. The example level 2 data products is displayed over this slide. The product parameters are also mentioned here. The right hand side image represents the integrated water vapor in layer 3. The left hand side image represents the specific humidity in 6 selected layers. The level 3 products are global grid product, which is defined at grid interval of 0.1 degree. It is associated only to the area of interest over the Indian region. The product are generated after each and every dump acquired. However, they are archived only twice in a day at 00 hours GMT and 12 hours GMT. These product represents all the acquired dump during this period of 12 hours. The product parameter are also mentioned on this slide. The images attached to this slide represents the brightness temperature and integrated water vapor parameter of level 3 product corresponding to a recently acquired products. The MHS data products quality is jointly assessed by the user from a Space Application Center, NCMRWF Center, and MES. The brightness temperature product bears the radiometric sensitivity and geometric accuracy as per the specification and compliant to the application requirement. The humidity product bears the geophysical parameter sensitivity and geometric accuracy as per the specification and compliant to the application requirement. The quality of product has found suitable for assimilating the numerical weather prediction model. With this, the mission has achieved its planned goal for future ISRO mission, and it is end of my presentation. Thank you.
Welcome to everyone. My name is Shukla. I am honored to stand before you today at IEEE InGARSS to share insight and perspective on a comparative assessment of estimation of precipitable water vapor PWE using scientific software GAMIT and IIIT AR. These are my content, motivation, introduction, research objective, study area, methodology, result, conclusion, and reference. Motivation, sufficient availability of Earth observation data need to be utilized for weather monitoring. Genesis drive PW is an efficient way to estimate atmospheric water vapor. Accurate PWE is essential in weather monitoring nowadays. PW is the widely integrated amount of water vapor in the atmosphere. It is a valuable predictor for weather forecasting. It's my introduction part. A detailed analysis of humidity field is important precondition for better monitoring of local regional extreme precipitation events or forecasting with improved by spatial resolution. Genesis processing involved in relation of many different sources of error. The raw measurement by the Genesis not contain true range. These are my following research objective to estimate PWE using open source different triple-P processing software environment, right triple-P, and using scientific GPS processing noise software GAMIT for genus URS at MIT Prayagraj and UNESCO based network processing scheme. Both GPS only and combined GPS and GIS observation file. Second is to perform time series comparison obtained PWE value for gamete of triple PR. And third is to statically estimate the consistency to generate finding with the appropriate PW value derived from the radiation data. These are my study area. My first study area, our college campus MIT Allahabad, and this second study area I have to chosen network based UNESCO. This flowchart shows the methodology on how to estimate PWE. Different science software GAMIT and triple PAR network based processing using GAMIT. The development of GAMIT was a group effort that include researchers from the MIT as well as astronaut and marine biology. This tool, which is based on GPS, may be used to estimate station coordinate and velocity, function rendering and post-earthquake deformation, atmosphere delays, satellite orbit at the orientation corrected by utilizing GPS signal. This operating system must support X windows for the programming work correctly. Single station processing flight triple P. Flight triple P make it easier for relevant research application development to the place. The vast part flight triple P diverse resolution of ambiguity add single station processing on different GPS data. The analysis of GPS data result in ambiguity estimation both large land and tides for the solution. While least square arrangement, the main method determine the known parameter data cleaning and uncover inaccuracies. Find cycle have to be skipped through. These are a result section. The results have been obtained from both the processing the software product gamut and practical. The result have been separated by different stations present in the below graph. The graph is showing that a remissive value of gamut and right triple PAR. PWB graph shows above follow the general trend of PWB obtained for meteorological source using RMSC have been calculated between PW obtained from the difference of the product and once obtained from the meteorological source, the RMSC value of two difference of the product then be compared. In the region of South California, out of observation made of 10 station observation of 5 stations with the smaller RMSC value gamut and observation the remaining 5 stations shows smaller RMSC value of triple P. In the region East Uttar Pradesh MNIT station only observation made is smaller RMSC value gamut compared triple P AR. It can also observe in the region of South California station TBL CHL shows the large systematic value of PW obtained genesis position compared to PWB meteorological source. Conclusion: the following conclusion have been drawn from the research work. From PWB resolution obtained 10 stations South California that PWB generated from positioning solution by gamut have been found to closure value reportedly meteorological sensor the same region same time for some station. This PWB exhibited regionally small RMSC the moderate correlation between gamut obtained PWB meteorological PWB. Some station exhibit a large systematic error for their PWB graph. The follow the general trend of meteorological PWB graph. The PW obtained from the positional should triple PR also as follow general trend. The graph obtained from the meteorological PWB they experience higher overall RMSC. The PW result obtained from one station 90 exhibit RMSC lower correlation in the given obtained PWB large RMSC higher correlation in case of triple PR obtained PW. For the case of 90 there was only one station whose PW value compared to meteorological PW value. These are references. Thank you.
Basically, in CSR4PI, we are doing research in the fields of crustal deformation, precipitable water vapor, and ionosphere using GNSS, that is Global Navigation Satellite System. For the first time, comprehensive noise analysis is carried out using only GPS, LONAS, and combined time series. Using the multi-GNSS geodetic grade reference receiver data, best suited noise model is computed and the noise amplitudes with uncertainties are calculated in this paper. Basically, in this field, noise analysis has been carried out using only GPS data. So noise in GNSS is a combination of white noise and time correlated noise. White noise is a random signal which is uncorrelated in time with equal intensity at all frequencies. Time correlated noise is generally distinguished by power law noise models. White noise can be reduced by repeated or long measurements, whereas flicker noise and random walk noise dominates with an increasing data span. Several studies have been carried out, but there is no final consensus about the best fit noise model for the GPS time series. So in this paper, we had analyzed the data of about 15 multi-GNSS stations during 2015 to 2021 in and around Indian subcontinent. In that, three CGNSS stations and 12 IGS stations. IGS stations are marked in red color, red star, and the blue triangle shows the CGNSS stations, which is part of our network. This data is processed using Benny GNSS software. Benny is a software designed by University of Bern, Switzerland. Process and estimate the noise in the time series, maximum likelihood estimation, and spectral analysis performed using the Hector software. Maximum likelihood is used to estimate the noise component and measure the amplitudes of noise present by considering the annual seasonal signal in the time series. Hector software is used to determine MLE, PhD, noise amplitudes, and velocity uncertainties. It is a C++ language Unix-based software which supports the maximum likelihood estimation and spectrum analysis. So maximum likelihood is used to estimate the noise component and measure the noise amplitude using the linear functional likelihood L that is shown in this equation. In the spectrum analysis, signals are analyzed in the frequency domain. So using this, calculated the various components of the noise, that is where maximum likelihood values are used, computed using the maximum likelihood estimation method to characterize the dominant model. So MLL is an indicator that shows the degree of coherence between observed data and assumed noise model, based on which the best noise model is selected. So we had calculated for our various stations the maximum MLL values, and it is plotted in this for the north, east, and up components. So it has been observed that power law noise in MLL values of power law noise are more for all the stations, which shows that the best fit noise model is power law noise. So after the MLL, we calculated the archaic information criterion and Bayesian information criterion to check the best noise model. So it has been shown that low values of AC and BC has confirmed the power law noise as the best fit model. So now it has been confirmed that the power law noise is the best fit model out of, as we know that power law noise is a combination of flicker noise and random walk noise. We had calculated the spectral indices, so which has shown that spectral index of -1. And we had shown the power spectral density of two stations, that is Roorkee and NIOT, GPS, GLONASS, and GL, north, east, and up components. So we can see that the best with residual, there is a best fit is for flicker noise. So which shows that the flicker noise is the best model. And these results again, it has been confirmed using the MLL, AAC, and BAC. Best noise fit of our model is a flicker noise. We have calculated the amplitude in north, east, and up components, and it has been plotted in this figure. It has been observed. We can observe that amplitudes are lowest in the north components of GLONASS time series, which can be attributed to the less scatter compared to the GPS and GLONASS combined time series. And also it can be attributed to the high frequencies of GLONASS satellites, since the flicker noise decreases with an increase in the frequency. Also, we can observe that in the east component, errors are comparatively less for all the time series, that is standalone GPS, GLONASS, and combined time series, compared to the north and east component. So that is around approximately 13 mm. And also we can observe that noise is highest in the up component compared to the north and east components. Yeah. So after calculating the noise amplitudes, we had calculated the velocity uncertainties. Velocity uncertainties also show the similar trend as amplitudes, that is less in the north component of GLONASS time series, and overall uncertainties are less in the east component compared to the north and up component, and higher uncertainties in the up component compared to the north and east. So here we had shown the number of days of data used for processing in this analysis. Number of days, that is 1902, 1505, and so on. So we can observe the stations with more that is more than nearly 5 years of data have less uncertainties, that is Coco, Hyderabad, Lhasa. So which confirms that uncertainties depend on the data span and the preferred noise amplitudes. So we can conclude that flicker noise model is the best preferred model For all the time series, that is GPS, LONAS, and combined time series, amplitudes and uncertainties are less in Earth component. All the time series have comparatively less amplitudes and uncertainties. Indian time series have higher amplitudes and uncertainties, depicting that combined analysis does not benefit. Stations in southern hemisphere are not significantly noisier than northern hemisphere stations. Uncertainties are less for the station with approximately 5 years of. So using this work, we are planning to expand this for the other analysis. That is, we should carry it out for longer span of data to assess the random walk noise model. Also to understand the impact of assumed noise models on the velocity estimation, especially in the plate boundary regions. I would like to thank HCSR for supporting the GNSS program. Others also thank program aides and organizers of INGARSS 2020.
So you are mentioning, you are concluding that about the uncertainties for 5 years, but what are all observations which you have that may change if we are taking the data over the longer span, right?
Yes, ma'am. If your data is longer span, we will get uncertainties are less. So it means that we will get some precise position estimations. If data is more, we will get precise position estimation.
Yeah, so this is time being, this is for the data which you are considered, so, but this is not a generic statement which we can make, right?
Means actually whatever data available, we did the analysis, ma'am. So
This is for 5 years. Maybe if it is 10 years or so, or maybe higher.
yes, ma'am.
Yeah, the observations might be different, right?
Yes, ma'am. If it is data increasing 10 years, 15 years, that uncertainty will still less, ma'am.
So we conclude the session 4 of track 5. I would like to thank the session chairs, Dr. Subhadip Dey and Sangeeta Chaudhary. And I would like to also thank all the participants for their research talks.